Ever feel like you're staring at a mountain of information and just wish you could instantly grab the coolest nuggets?
Yeah, the aha moments without all the wading through stuff.
Exactly. That's the sweet spot we aim for here on the deep dive. Your shortcut to getting seriously informed. And today's dive is particularly electrifying, tailored just for you.
Absolutely. We're plunging into the intriguing world of unconventional hydrocarbon resources.
Unconventional, so not the usual spots.
Right. Think oil and gas hiding in unexpected places like crystalline basement rocks. And the real hook, a technology called RALF1 that's potentially shaking up how we might find them.
Okay, RALF1. Got it. And to fuel this exploration, we've got a really fascinating mix of intel, haven't we?
We do. We're talking scientific papers, get this, in Ukrainian, Russian, and English.
Wow, multilingual.
Plus a peek under the hood at some software code, presentation slides just packed with data, and even a news report transcript in Italian.
It's like a global puzzle we're piecing together for you.
Mm-hmm. And our mission really is to synthesize all of this diverse information to understand the science behind RALF1.
And its potential, right, for sniffing out hydrocarbons in these non-traditional geological settings.
Exactly. We'll be focusing on a spot in Ukraine, the Ravaruska epirogenic zone.
Ravaruska, okay.
And drawing some, I think, pretty compelling parallels with a study in Vietnam and the very well-known White Tiger oil field.
Okay, so let's start there. Most of us, when we think oil and gas, we picture those, classic layers of sedimentary rock.
That's the standard picture, yeah.
So why are we suddenly digging into what sounds like the Earth's harder, more fundamental crust? The crystalline stuff?
You're right. The traditional focus has been on sedimentary basins. That's where the organic matter usually cooks, basically.
All right.
But the thinking is evolving. We're realizing that significant hydrocarbon deposits can also reside within these crystalline basement rocks.
Things like granite.
Exactly, like gabbro, granite, those hard foundational rocks that make up the continents and their submerged shelves.
And these aren't just rare flukes.
Apparently not. They've been found sort of all over the globe, on all continents, really.
That's a major plot twist in how we think about energy resources.
It really is.
And this brings us to Ukraine and the Ravaruska zone you mentioned. What makes this area so interesting in this new light?
Well, the Ravaruska epirogenic zone, it's in the Lviv region of Ukraine. It sits along this just colossal geological fault line.
How long?
Over 4,000 kilometers, stretching from way down near the Iran-Iraq border.
Wow.
And what's truly fascinating is this geological cousin structure. It's very likely the White Tiger field off Vietnam's coast.
Okay. And White Tiger is significant.
Hugely significant. That field boasts proven oil reserves exceeding 88 billion cubic meters, all trapped within oil-saturated granitoids.
In granite-like rocks, not sediment.
Correct. And they've already pulled out something like 100 million tons. So the tantalizing prospect is that Ravaruska, being structurally similar, could hold a similar kind of bounty.
So it's like finding a geological twin that's already a proven winner.
Kind of, yeah. That's the hope, anyway.
What are the clues on the ground, then? In Ravaruska, what's the Earth telling us that hints at this potential?
The geophysical data from the Ravaruska area is showing some, compelling signals. We're seeing thermal anomalies.
Heat.
Yeah, imagine heat rising from deep within the Earth, likely channeled along these major fault lines.
Okay.
We also observe anomalously low gravity readings right over these specific uplifted crystalline basement rocks.
Less gravity than expected. Why is that significant?
It often indicates that the rocks underneath are less dense than their surroundings, which can sometimes be associated with certain geological structures or potentially fluid content that might include hydrocarbons. These are the kind of geophysical breadcrumbs,
Breadcrumbs leading towards the potential treasure.
Yes,
okay.
Exactly. They point towards significant structures and maybe hydrocarbon accumulation.
Okay, so we've got this intriguing location, Ravaruska, with some promising whispers from the Earth. Now let's get into the tech that might unlock these unconventional resources. RALF1. What exactly is this technology designed to do?
So RALF1 is described as a technology specifically designed to study key characteristics, forecast parameters, they call them, of potential hydrocarbon reservoirs or collectors.
Key characteristics like what?
Things like resistivity. That's how much the rock resists electricity flow.
Okay.
Then there's the anisotropy of resistivity. That's like understanding if electricity flows easier in one direction through the rock than another. Think wood grain, maybe.
Okay, direction matters.
It can, yeah. And also polarizability. That's the rock's ability to store electrical energy temporarily when you zap it with an electric field, like a tiny temporary battery in the ground.
So it's essentially listening to the electrical personality of the rocks deep beneath our feet.
That's a good way to put it.
How does it do that listening?
It analyzes electromagnetic fields to build a picture, a map really, of the geoelectric layers underground.
How deep can it see?
It claims to be able to see down to depths of 10 kilometers or even more.
10 kilometers, that's deep.
It is. And RALF1 looks for specific signs. Local increases in resistivity, because oil and gas don't conduct electricity well, certainly not compared to salty water.
Right, they insulate.
Correct. And it also looks for a decrease in polarizability compared to water-saturated rocks.
Interesting. Has this been tested much?
The sources indicate, yes, significant field testing. Over 20,000 linear kilometers of profiles.
Wow.
Across something like 60 promising areas.
That's a serious amount of road testing, or ground testing, I guess.
Definitely suggests a level of maturity.
So what's the core idea behind how RALF1 manages this feat of subterranean detective work?
The fundamental principle seems to involve a mathematical approach. It's about mapping the effects of Lorentz forces.
Lorentz forces, remind me.
Those are the forces that act on moving electrical charges when they're in magnetic fields. Basic physics, but applied here in a novel way.
Okay.
So it maps the sort of compact action of these forces into a compact property of the physical body or space itself, like the rock layers.
Mathematically, without direct physical interaction.
That seems to be the claim. Think of it as the technology listening to the universe's electromagnetic whispers in a completely new way, potentially unlocking hidden information.
That sounds ambitious.
It is. And the really mind-bending part is that the developers believe this approach isn't just for geology. They suggest applications far beyond finding oil, like solid-state physics, nuclear physics, even medicine, and maybe improving numerical methods in computing.
That's an unexpectedly broad reach, just from analyzing electromagnetic fields.
Based on this core mathematical principle, yeah. It's a big claim.
Okay. Now, when we think about how we usually explore what's underground, geophysics, what makes RALF1 different from those traditional methods?
Well, traditional methods like, say, vertical electrical sounding, VES, they've been around a long time. They work, but they can struggle sometimes, especially in areas where you've got a layer of conductive material near the surface, like certain clays or salty groundwater. It can kind of mask the signals from deeper down.
Like static obscuring a radio station.
Right. Exactly. RALF1, on the other hand, is described as a high-resolution electromagnetic exploration method with induced polarization, HRES-IP for short.
HRES-IP. There.
Think of it as a much more detailed way of sending and reading electromagnetic signals in the ground. The aim is really to cut through those limitations, cut through the static, and directly examine the properties of the potential reservoirs themselves.
So HRES-IP is a key part of the RALF1 toolkit.
Seems to be, yes.
What kind of insights does this detailed electromagnetic listening provide? What does the data tell you?
The data from HRES-IP, which RALS1 utilizes, is said to offer a really rich data set. It can help rank potential geological structures, which ones look most promising.
Prioritize targets.
Right. Understand the lithofacial characteristics. That's basically the types of rocks and how they're arranged, within these potential trends.
The nitty-gritty details.
It also allows for detailed mapping to predict how saturated the rocks might be with oil or gas. Mapping the boundaries of these zones, identifying faults.
Faults are important.
Crucial. And estimating the actual oil content based on those resistivity and polarizability measurements we talked about.
And what kind of gear, what hardware is involved in actually gathering this electromagnetic data from the ground?
The equipment mentioned includes a computerized generating array that creates the electromagnetic field they send into the ground.
The transmitter.
Essentially. Along with current registration, so they know precisely what signal they're putting in.
And on the receiving end?
There's a multi-channel recording system. One source mentioned a name, AGEXXL. It measures the returning signals across a wide frequency range from direct current, DC, up to 500 hertz.
And getting the timing right must be critical.
Absolutely.
Yeah.
The whole system is synchronized using GPS for very precise data correlation between the transmitter and all the receivers.
Okay. You mentioned earlier that RALF1 uses mathematical analysis of the return signals. How does that help interpret the data? Does it sidestep some challenges of older methods?
That's a key point the sources emphasize. RALF1 apparently relies heavily on sophisticated mathematical analysis of the signals that come back from the subsurface.
Instead of just physical models.
The idea seems to be that this mathematical focus can potentially reduce the need for really complex physical simulations of the subsurface.
Which can be tricky.
They always involve making assumptions, right?
Huh?
About the geology, the physics, and those assumptions can introduce biases into the results.
Garbage in, garbage out, potentially.
Kind of. So this approach, it aligns a bit with the principle of Occam's razor.
The simplest explanation.
That fits the data is often the best. By directly analyzing the signals mathematically, RALF1 aims for a more direct, perhaps less assumption-heavy interpretation of what's actually happening underground.
Interesting approach. So who might be interested in using this kind of, well, cutting-edge tech? Any specific companies or people involved?
The Hordotska Naftogazova company, which operates in that Lviv area of Ukraine, is mentioned as a potential adopter. Makes sense, given their location right in the Rovaruska zone.
And individuals.
The key figure associated with developing RALF1 seems to be Vadim Chernov.
Chernov, okay.
He's linked to a patent for the technology, number 2I116127-1.RF. And he apparently has a long history over 30 years working specifically with electromagnetic data.
So, deep experience.
Yeah, combining expertise in geophysics with computer programming.
And speaking of programming, we even got a glimpse into some Python software code that might be connected to RALF1, didn't we?
We did, yeah. Likely developed by Chernov. Analyzing that code revealed some interesting things.
Like what?
Well, the use of some pretty advanced computational techniques. We saw custom random number generators.
Why random numbers?
Could be used for simulating variations in geophysical measurements, maybe for Monte Carlo type analysis, or perhaps certain data processing techniques. It's hard to say for sure without more context.
Okay, what else?
Data filtering functions, definitely.
Yeah.
Including Fourier transforms. Those are vital for breaking down the electromagnetic signals into their different frequency components.
Which is key for RALF1's frequency analysis approach you mentioned.
Exactly. The code also uses parallel processing, likely to handle the potentially massive data sets efficiently.
Makes sense.
And it relies on powerful standard scientific computing libraries. NumPy, Pandas, SciPy, the usual suspects for heavy-duty data work in Python.
So, in theory, could this kind of software, this mathematical approach, be applied elsewhere? Like those granite formations you mentioned earlier, maybe in Pakistan?
Theoretically, yes. The underlying principles in the software architecture could potentially be adapted for hydrocarbon exploration in similar geological settings. Those granite formations in northern Pakistan were mentioned in one source as an analogous area.
But there's always a but.
Well, the real-world success, it always depends heavily on the quality of the data you can collect in those different areas.
Right, data is king.
And ultimately, it depends on further validation and, frankly, wider acceptance of the RALF1 technology itself within the broader geophysics community. It's still relatively new, it seems.
Gotcha. Now, it seems the claims around RALF1 stretch even beyond finding oil and gas. I remember reading something about predicting other kinds of events. That sounds pretty wild.
It does, doesn't it?
Yeah.
But yes, that's correct. Some sources report that RALF1, or the underlying mathematical method, has been used to make predictions in areas that seem totally removed from geology.
Like what?
Like fluctuations in cryptocurrency prices.
Seriously? Crypto?
Yeah. And even predicting spikes in oil prices following specific geopolitical events, like drone attacks.
How would that even work?
The connection isn't clearly explained in the sources we had, but the implication is that the mathematical framework for analyzing complex system signals might be broadly applicable. There are even mentions of potential uses in meteorology weather prediction.
So analyzing complex patterns, whether they're underground electrical fields or market movements or weather systems.
That seems to be the underlying idea, however speculative it might sound for some of those applications.
Okay, this brings us back maybe to the fundamental geophysics. You mentioned induced polarization, IP, earlier. Can you unpack that a bit more? How does it work and how does RALF1 use it?
Sure. Induced polarization, IP, is basically the ability of Earth materials to temporarily store electrical energy when you pass a current through them. Think of the ground acting like a mixture of resistors and capacitors.
Storing charge for a bit.
Exactly. Now, RALF1 technology incorporates something called frequency sounding of induced polarization, or AFS-IP-3D.
AFS-IP-3D, another acronym.
Yep. This technique allows them to measure how resistivity, that anisotropy we talked about, and the polarizability change across a whole spectrum of frequencies.
Not just one measurement, but how it behaves at different frequencies.
Right. And that frequency-dependent behavior can provide much richer, more diagnostic information about the subsurface, the rock types, the fluids, compared to just measuring resistance to a simple, steady current, like basic DC resistivity.
And how deep can these IP techniques typically see?
Well, traditional IP surveys, especially when they're aiming deep, often use specific setups like magnetic dipoles or long grounded dipoles to transmit and receive the signals. These can potentially probe depths down to around, say, 6 kilometers for IP measurements.
Still pretty deep.
Oh, yeah. Now, while RALF1 is also an electromagnetic method using IP principles, it seems to place more emphasis on analyzing those frequency-dependent responses directly.
As opposed
to, say, traditional time domain IP, which often focuses more on measuring how quickly the stored voltage decays after you turn the current off. RALF1 seems more focused on the live response across different frequencies.
different ways to analyze that polarization effect.
Exactly. And it's worth remembering, too, that just basic low-frequency electrical surveying is a foundational geophysical method for detecting hydrocarbon deposits anyway.
Why is that?
Because oil and gas accumulations represent a pretty significant change, a heterogeneity in the Earth's natural electrical properties compared to the surrounding water-bearing rocks. RALF1 just aims to leverage these fundamental principles in a perhaps more sophisticated, high-resolution way.
Okay. So bringing it all back to Ukraine, what could the successful deployment of a technology like RALF1 actually mean for the country, especially given its current energy situation?
Well, if technologies like RALF1 can be successfully applied there, if they can reliably locate and help target local hydrocarbon resources in places like Roveruska,
It could be significant.
it could have really significant positive impacts on Ukraine's energy security. It could potentially lessen their reliance on energy imports or on needing vast amounts of storage. It boosts energy independence.
And the geology itself provides a strong rationale.
Absolutely. Those geological parallels we discussed between the Roveruska zone and proven oil-rich basement rock areas like Vietnam's White Tiger Field, the similar basement uplifts, the deep fault systems, those shared thermal and gravitational anomalies, they provide a really compelling scientific reason to explore further using these kinds of advanced techniques.
It's truly a fascinating intersection, isn't it? You've got geology that kind of defies the traditional textbook picture.
Right, oil and granite.
And then this technology, RALF1, that seems to be pushing at the boundaries of what we thought was possible in subsurface exploration and maybe even beyond.
It really is. The idea that a system initially designed, it seems, to find oil could offer insights into such a diverse range of predictive challenges.
Yeah.
It's quite something to wrap your head around.
Yeah, it really is.
Indeed. It leaves you pondering a rather profound question, I think.
It just...
If a technology, or maybe the mathematical thinking behind it, developed for oil exploration, can potentially provide a new lens to understand and maybe even predict events across these seemingly unrelated complex systems.
Like finance, meteorology.
Right, geology, finance, meteorology, maybe medicine. What other fields could be fundamentally transformed by such a data analysis and prediction paradigm?
That really sparks the imagination, doesn't it, about the potential for future exploration and discovery.
In the most unexpected corners of knowledge.
Absolutely. It just underscores that never-ending human quest to understand the world around us, and those thrilling moments when, seemingly disparate fields suddenly converge in surprising, maybe even revolutionary ways. Thanks for taking that deep dive with us.